it's 1:35, so let's get started. In the last class, we discussed two important concepts, resolution and the contrast of SEM. Today, we're moving into a new topic. We'll look at the instrumentation of SEM. Before going into the details, something we're going to cover, the electron guns, I'll give you a big picture what SEM looks like. So for SEM, as well as TEM, if you take the class later, you can draw that schematically. So you have the first part. The first part is the column. And you can draw the second part. The second part is the specimen chamber. On the very top, we have the electron gun. The purpose of having electron gun is to generate electrons. Since we're using SEM, we need electrons to create images. So we need a source to create electrons. Then after electrons, you will see some lenses. That's something we'll cover in details next week. In the specimen chamber, it's pretty simple. So we have the specimen down here. Usually it's mounted on the stub. The most simple SEM has one detector. It's called SE detector. So let's insert a detector here. Detector. SE stands for secondary electrons. We'll cover that in a few weeks. When the electron beam leaves the electron gun and passes through the lenses, it will hit the specimen. And the electron beam specimen interaction will generate all sorts of signals. Then the secondary electrons will be captured by the secondary electron detector. So this is SEM in a big picture. You can insert a lot more other detectors like backscattered electron detectors, EDS detectors, EBSE detectors. All these detectors we'll discuss in details. I just realized I've got to label these are lens systems. Today, we'll focus on the electron guns. As we mentioned before, the purpose of having the electron gun is to create electrons. But let's be more specific and write that down. So the purpose is to create not any electrons, but to create a narrow and intensive beam of electrons. Let me ask you, why do we want the electron beam to be narrow? Why? Yeah, but if you use a word, a term we learned last week, why we want... Excellent, I heard better resolution. So the narrow electron beam will give you better resolution. Okay, then let me ask you, why do we want something intense, something really bright? Why we want like not only narrow, but intense? There's another term we discussed in the class last week.
Better contrast?
Better contrast, yes, but I was looking for another term. Intense does not guarantee you like a better spot size. Narrow gives you a better spot size. But why intense?
Get past the noise?
Excellent, excellent. So in this case, if the beam is intense, we'll get better signal to noise ratio. So better signal to noise ratio, or just say SNR, a signal to noise ratio. Anything you do, like any branch of science you do, if you have a lot of data, you'll have some information, you'll have some noise. So what is the useful information? What is the noise? You need to know that. In SEM specifically, by creating a bright beam, an intense beam, you're able to increase signal to noise ratio. Okay, so if we look at the electron guns, there are 3 types of electron guns. So 3 types of electron guns. The first type is called thermionic. Basically, it means thermal. As the name suggests, if it's purely thermal, then the electrons are generated by heat. So in this case, it's only heat. The second type of electrons, the second type of electron guns, we can call it cold field emission gun. Cold field emission. In this case, the electron source usually operates at room temperature. You can slightly increase the temperature, but never to the degree where you use the thermionic gun. So for the cold field emission gun, it's mainly voltage or potential. Let's quickly compare the first type and the second type. In the first type, you use a lot of heat to heat up like a piece of metal. Then the electrons will be kind of like free to move. Then you apply an electric field, you apply a bias, electrons can be emitted from the material. So this is largely by heat. In the cold field emission gun, what happens is it's at room temperature. You generate an intense electric field to pull electrons out one by one. Can you see the difference? One is thermal assisted, another is less thermal assisted. The third type is a combination. The name is called Schottky emission. It's a combination of heat and electric field. In the second case and in the third case, because we use field to generate electrons, so those are called FAG. In SEMs, like when you use the instrument, people will tell you whether it's a FAG or not. So FEG. FAG stands for field emission gun. So I'll just write down the full name. In fact, most of the SEMs we use nowadays, the guns are FAG, not tungsten. When I was a grad student, the first SEM I learned was with the tungsten filament. But as far as I know, all the SEMs on campus, on Texas A&M campus, all of them are field emission guns. Maybe the Phenom is still equipped with tungsten filament, the desktop SEM. But in the user facilities, like the instruments at MIC, MCF, and EGIFAB, if not 100% of the instruments are field emission guns, at least 95% of the instruments are field emission guns. Let's look at the three types guns one by one. So the first type is thermionic. What you have is you have a tungsten filament, and you bend it. It forms like a hairpin structure. I'm just drawing part of the tungsten filament. It's very similar to the old light bulbs you see. When you have those old light bulbs, you pass electron or you pass current through the filament. It gets really hot, and it will generate a lot of photons. So it's a very similar idea. It's a very similar idea. So what you do is you pass current through that to heat up the filament. Underneath the filament, there's a structure called Winnell cup. So this is called Winnell. It applies a bias. The electrons, after getting heated up, they're so ready to leave, but like you need like a small kick to get these electrons out. Then the Winnell cup applies a bias to extract electrons out. As the name suggests, it's called thermionic gun. So the filament temperature usually is around 2,700 degrees Celsius. So it's very, very hot. It's very, very hot. Any guesses why people use tungsten rather than other materials for thermionic gun? Exactly. Exactly, melting point. The melting point of tungsten. So the tungsten is 3,422 degrees Celsius. Most metals, they melt at such high temperature, but tungsten is able to withstand the heat. That's why tungsten is used. Some of you are from material science background, or with like you do metallurgy field research. Let me ask you, when the filament fails, when the filament breaks, any guesses? Usually where the breaking happens? As a material scientist student, any guesses? Think about it, like in a material, if something snaps, where is likely to be the breaking point?
Shouldn't be at the
sharpest bend.
Compression side?
Compression side actually is less likely to break. Materials in general are stronger in compression, weaker in tension. Some materials, they don't have the asymmetry, but if you have a crack, if you apply tensile stress, the crack can propagate. But if you apply compressive stress, the crack can be arrested. Let me give you a hint, like a defect side. Then what would be what would be a common defect in a material?
Dislocation.
You're getting close,
Boundary.
very close. Grain boundary, exactly. People looked at like the broken filaments. What they found is usually the failure happens at the grain boundary. Very good. For thermionic sources, since you're not really using it anymore, I'll just verbally tell you some information. I will not write them down. For thermionic sources, you cannot leave the filament always on. Whenever you finish using the instrument, you need to turn that off. So you have to shut that down. Kind of like when you enter the room, you turn on the switch like of the light to light the other room. When you leave the room, you turn off the switch. It's very similar to this idea. You turn that off when you're not using it. The second thing is you cannot just switch on and it will just turn on straight away. You have to slowly ramp up. So you have to slowly increase the current manually until you get a saturated beam. But luckily, you guys don't really use this instrument anymore. So you don't have to worry too much about the operation side of the filament, of the tungsten semiotic filament. Let me write down the pros and cons of having the tungsten hairpin kind of guns. So let's write down the pros and the cons. For pros, first of all, it requires a less complex vacuum system. As grad students, you guys know vacuum is expensive, and better the vacuum, more expensive it gets. For the tungsten hairpin semiotic guns, the vacuum requirement is 10 to the minus 3 Pa. You will see in the later two cases what kind of vacuum we need. The second advantage is it's very cheap. It's so cheap that if you break one, you can afford it. So like, that's how cheap that is. And it's very easy to replace. So these are the two main advantages of using the tungsten filament or the tungsten hairpin semiotic gun. Then there are a number of disadvantages. The first is it has poor coherency. And this directly leads to poor resolution. That's one major drawback. We'll discuss that in details towards the end of the class today, like what it means by coherency and why it's important for the resolution of the instrument. The second thing is it has low brightness. When you have low brightness, the direct impact is you have poor signal to noise ratio. However, when you operate SEM, there's one way to combat that challenge. You can spend more time on each pixel. So the beam can dwell longer on each pixel. That means to improve the signal to noise ratio for each image, it takes longer to do. The third disadvantage is it has short lifetime.
Is there any change in the amount of heating you get in your sample depending on what kind of electron beam you're using?
That's a really good question. That's a really good question. Let's think about the where heat is coming from. If your material is a good conductor, then whatever heat dumped onto the specimen is able to carry the heat away. So it depends on our specimen first. Then if we fix a specimen and think about like electron beam interacting with the specimen, then it comes from the energy of the electrons. The energy of electrons, higher the energy of electrons, the more heat it's dumped into the material. So how to reduce the energy? You can do that by two ways. You can either reduce the voltage or reduce the current. Does this answer your question?
I believe so, yes.
Okay, by the way, the filament itself is very hot. The specimen is so far away from the filament, from the gun, so the heat from the gun does not affect your specimen.
I take it the low intensity on the tungsten filament probably correlates to maybe a little bit less sample heating than in some of the field emission guns?
You can say that. You can say that, but it's always a compromise. If you want to reduce the heating of the sample, then you don't get the signal to noise ratio, so you get a noisier image to look at. Does this make sense? In research, in many cases, you're trying to find a balance. When you ramp up something, you degrade another. So by reducing the sample heating, then you reduce the signal to noise ratio. Does this answer your question better?
Yes.
Okay, cool. Okay, so those are the characteristics of the field emission, not field emission gun, of the tungsten filament. Now let's move to the cold field emission gun, the one with only or largely field, not much heat, and look at how it works. Cold field emission. In this case, you don't get a hairpin shape kind of filament. Instead, you get a really pointy filament. Usually, the gun looks like that. And if you look at the apex of the tip, the radius R is usually tens of nanometers. Underneath, instead of having a Wanell cup, you have suppressor and the extractor. Again, the idea is to extract the electrons out. So the first one is suppressor. And this is extractor. When you apply, if you apply a voltage, very high voltage on the tip, so this is called FAG, F-E-G, and more specifically, it's cold FAG. When you apply a very large electrical current, electrical voltage on that, let's say 10 kV, then a very strong field will be generated. So you apply a large voltage, then a strong field is generated. There's a relationship of the strength of the electric field and the tip radius. The strength of the electric field is proportional to 1/R. So the sharper the radius, higher the electric field. Then the electric field, when it's large enough, it will be able to kick out the electrons, and these electrons can be extracted and accelerated in the column. In this case, not much heat is involved. It's really the high voltage on the tip doing the work. Let's look at the voltage again. In SEM, we usually use 5 keV to 30 keV, depends on the application. Again, we'll discuss like on the in what circumstances you use low keV, in what circumstances you use high keV, but it's in kilovolts range or tens of kilovolts range. What is the household voltage in the United States? No answer?
110.
It should be around 120 to 140 volts. So having 10 kV versus 100 V, that's orders of magnitude difference. So the voltage you apply on the electron gun on the tip is very, very high compared to the household voltage. Let's also look at the the material. Oh, excellent. What's the material? The materials, again, tungsten. Yeah, but to be more specific, it's a single crystal tungsten. So there's no grain boundaries. Remember we said in the thermionic filaments, the hairpin guns, usually it breaks at grain boundaries. For those field emission guns, people use single crystal tungsten filaments, and you'll see why. Instead of using the polycrystalline material, they use the single crystal. Let's look at the pros and the cons.
A quick question. What
Sure.
is the suppressor and the
Oh, okay. The suppressor and the extractor, they work in harmony. So suppressor actually decelerates the electrons. Extractor accelerates the electrons. The idea is to do like a fine balance of the electrons that allows a crossover. So what this setup is trying to do is to make electrons cross or focus to a single point for the first time before they focus again in the along the optics. Does this make sense?
Okay, yeah.
Okay, yeah, thank you.
Okay, no worries. In the next class, you will see the electron beam crossing a number of times, and which eventually gives you the image. Okay. Back to the pros and the cons. For the cold fag, it gives you very high brightness. In another word, you get much, much better signal to noise ratio. The second advantage is it gives you the best coherency. And that also gives you the best resolution among the three types of guns. The third advantage is it has very long service life, so long lifetime. Usually it's about 5,000 hours. Remember, in the regular tungsten thermionic guns, it's 100 hours. So the cold fag is 50 times better in terms of longevity.
Do they ever use crystal filaments in the thermionic?
I don't think so. The reason is because the towards the end of the class, I'll show some PowerPoint slides. You will see the filament is actually pretty large. That's why it's expensive to create a single crystal, like a large single crystal tungsten that you can bend into filament. So as far as I know, people don't use single crystal filament for the thermionic applications. Okay, and another feature which is very good, it never turns off. Remember in the lab demo last week, I said, I'll turn on the beam. Then I corrected myself. Then I said, we never turn off the beam. What I did was not to turn on the beam, but to open the gun valve. Basically, just remove a metal that blocks the beam. And that's just one click of the button. For fag guns, you never turn off the beam. The beam is always on. It's more like in the room which has no windows. You go into the room, you don't turn on the light is always on. But when you open the door, some light will come out.
So what happens if it loses power?
In theory, there is a backup generator. So what happens in university and in many companies, especially if they have those very expensive instruments, they never rely on the commercial power grid. They always have like a backup generator. Whenever you lose the power, then the backup generator will kick in. Then you have usually 20 minutes to an hour, depends on what system you have, to manually turn off all the systems.
Yeah, we had something like that happen where the backup power supply died.
Mm-hmm.
And the end seems fine.
Mm-hmm. Yeah,
So
in most of the
what's
cases. Go on.
I was going to say, when it does lose power, what could happen?
There are two scenarios. The first scenario is the gun valve is closed. Then in this case, you don't have to worry about it because the gun chamber, like where the gun sits, is always kept at a very high vacuum. If the vacuum degrades slightly, it's okay. It's bad to the gun, but it's not like terribly bad. If you had the gun valve open, then you may run into trouble, and the power surge may destroy your filament because you don't keep the gun chamber in a very high vacuum. In theory, it should not happen, but if unfortunately that happens, too bad, you have to change the filament. Does this answer your question?
Yep.
Okay, cool. So we've talked enough about the advantages, the pros of the cold vac. Then what are the disadvantages? The first disadvantage is that requires extremely high vacuum. If I put that in numbers, it needs to be 10 to the power of -9 Pa. Remember, for tungsten filament, like the first case, semiotic case, all you need is 10 to the -3. Now you need 10 to the -9. And the vacuum system can be very expensive. The second issue is you need to do periodic flashing. I'll put a quotation mark on flashing. What happens is, because your gun is kept at a low temperature, like at room temperature, then the vacuum can never be perfect. There's always some dirt floating around. There's always a chance some dirt will hit the gun and attach on the gun surface. So over time, the gun is getting dirtier and dirtier. So you need to increase the voltage, and basically you turn up the extractor to flash, to clean the gun tip surface. This costs labor, this costs time. So I list that as a disadvantage. The third thing is more critical. It's very, very expensive. I couldn't recall exactly how much it costs, but definitely you don't want to break one of these. If you break one of these, most likely you cannot afford it, and your advisor will be very mad. Okay, so this is the second type of electron guns. Let's move to the third type. The third type is easy. It's a combination of heat and field. So it's called Schottky emission. And this is the most common electron sources we use nowadays. In this case, it's heat plus field. There are two types of this gun. One is much older, another is more common nowadays. The older one, so I just say old. When I was a PhD student, that's what we used. You use a lab 6 single crystal. So it's called lab 6. It's lanthanum hexaboride. For the lanthanum hexaboride single crystal, you always form a very pointy tip. Then you apply heat, you apply electric field, electrons will be extracted from the tip. Then nowadays, the ones you guys most likely are using, those are very similar to the cold fag. In fact, like most of the design aspects are similar to the cold fag. As I said before, it's using a tungsten single crystal. And if you use heat, you use electric field, the electrons will be extracted out from the tip. Not surprisingly, the Schottky emission, like the regular fag, it sits somewhere between the tungsten filament and the cold fag. So let's write down the pros and cons of this type of electron guns. So this one has good coherency. So we have good resolution. It's better than the tungsten hairpin filament. It's actually way better than the tungsten hairpin filaments, but not as good as the cold fag. And also we have good brightness. Again, it's in the middle ground. And if we use the new one, it never turns off. For the old one, for lab 6, you still turn that off when you're not using it. But for the new design, the new fag guns, the ones we use nowadays, we never turn these off. There are a few cons as well. The first is it requires good vacuum. The tungsten hairpins 10 to the -3, the cold fags 10 to the -9. Any guesses what is the vacuum for Schottky emission, the regular fag? Somewhere in between. Anyone?
-5?
Close enough, 6, yeah, -6. So for this, you need 10 to the -6 part. Kind of like right in the middle between the tungsten hairpin and the cold fag. It has, I just realized I've got one advantage. It has also long lifetime. Long lifetime. It's an advantage. So it's about 5,000 hours. Okay. In terms of cost, it's also expensive. Not as expensive as the cold fag, but a lot more expensive than the tungsten hairpin filaments. Again, most of the SEMs we use nowadays, they use a regular fag, the Schottky emission gun. Any questions about these 3 types of guns? Some of them are ancient. You don't see them very often. Probably one day you'll see them in the museum. Some of them, we still use them today.
Yeah, so you said the new one, it's also tungsten, or is it?
The new one is also tungsten. So okay. To be specific, it's 001 tungsten single crystal.
And then you also said that the SEM Joule that we have at MCF is the cold field emission, right?
That's correct. As far as I know, like this is the only cold field emission gun we have at A&M. All the other instruments, such as the Helios in AgriFab, the Quanta in MIC, all of these are regular fag, not cold fag. The Lyra and the Ferra Tescan instruments are also regular fags.
Got it.
Okay.
So what kind of pump do they usually use to get down to that vacuum? Because like we have in the Army Research Lab, a little desktop SEM, which I'm assuming is probably a Schottky emission gun. And there's a roughing pump on it, but I know a roughing pump won't get down to anywhere near 10 to the -5. Do you know what kind of pump they would use in there? Is it like some kind of small turbo pump or diffusion pump, or?
That's a very good question. It's a combination of pumping systems. So you go down like each step with each pumping system. You're exactly right. The first pump you use is a roughing pump. roughing pump can help you get 10 to the minus 2, 10 to the minus 3. Then after that, there are a few designs. You can also use the diffusion pump to improve the vacuum to 10 to the minus 5, 10 to the minus 6, or you can use the turbo pump to improve the vacuum. To get extremely high vacuum, like 10 to the minus 9, then you need ion getter pump. So basically, you're doing sputtering. You're sputtering titanium ions, and titanium ions will just grab oxygen and the nitrogen air molecules and then hit or deposit on the other side. So it's a number of pumping systems working together, getting you to a very good vacuum. For pure SEM, to be honest, I haven't had a chance to have a close look. I don't know how many pumping systems it has. But if you look at the vacuum, if the vacuum is minus 3, then usually it's just a roughing pump. If the vacuum is minus 6, 10 to the minus 6, then you have to have either oil diffusion pump or you need to have a turbo pump. That's a very good question. Any other questions about these 3 types of electron guns, electron sources? If not, let's move on. We mentioned coherency a number of times. So let's look at what it means by coherency and why better coherency can give you a better resolution. For coherency, there are 2 types of coherencies. We only focus one type. There are 2 types. The first is called spatial coherency. The second type is called temporal. For SEM, we don't worry too much about temporal. We worry about spatial. So we'll only focus on spatial coherency here. Okay. Let's draw the schematics of these 3 types of filaments. So we have the tungsten hairpin filaments. We have the I'll just focus on the very tip. We have the regular fag. We have the cold fag. I'm putting regular fag in the middle because it's somewhere in between. Okay. So in the first case, when we use heat, since this bending, it's kind of over a pretty large area. So a lot of places they can emit electrons. Then the electrons are coming out from different places. They are spatially incoherent. That's why this one has poor spatial coherency. Then for the regular fag, so let's just say regular fag, this is tungsten filament. The last one is the cold fag. For regular fag, it's a combination of heat and the field. So of course, electrons will come out from the very tip, but also somewhere here, they can also generate electrons because heat can lower the barrier. So it has good coherency. In the cold fag, there's not much heat going on. What you're solely relying on or largely relying on is the electric field. The electric field concentrates at the very apex of the tip. So this one gives you excellent coherency. In SEM, in the next class, you will learn you can never converge the electron beam to a spot. You always get a disk. And the size of the disk depends on the image, depends on the spatial coherency. What you're getting is the image of your filament. So if the electrons are coming out from a very small area of the filament, then the probe is much smaller. That's why you get much better spatial resolution. If the electrons are coming out over a large area, then the probe is much bigger. You get a poor spatial resolution. Does this make sense? Yes? No? Or you need more digestion?
I have a question. So why would you ever use a Schottky instead of a cold field?
Cheap.
Okay, that's what I thought. Okay.
It's much cheaper, and also maintenance, like it's not that finicky. Plus, in terms of resolution improvement, you get some, but in most of the cases, you simply just don't need that level of resolution. If you're looking at, for example, nanoparticles, hundreds of nanometers, then maybe the regular FAC, like the Schottky, is good enough. But if you're looking at something super small, like super fine, tens of nanometers, then you need cold field, like cold FAC.
About what resolution can each of them achieve?
That's a really good question. That's a really good question. For regular FAC, for tungsten, I cannot remember anymore. It was so many years ago. I was either about your age or maybe even younger when I used tungsten filaments SEM. Then they just disappeared. For regular FAC, if you tune the beam really, really well, you can get about 1 to 2 nanometer spatial resolution. Then for cold FAC, if it's a really good gun, if you fine tune the beam, there is a possibility you can get about 1 nanometer or even sub-nanometer beam size. The SEM we use nowadays, the spot size is not an issue. But in many of the cases, in about 3-4 weeks, when we learn about the electron beam material interaction, you can make the beam super fine, but the signal you generate is over a volume underneath the beam. So the interaction volume is way bigger than the beam size. So your resolution is limited not by the beam, rather it's limited by the interaction volume. But having that's a good question. Having a good beam is the first step of getting good images. Any other questions about coherency and why better coherency leads to better resolution or better spot size? Okay, let's look at the very last topic relevant to what we learned today. Remember last week we had a very quick look at resolution. Today I want to take one step further to give you a bit more information. So let's just call closer look at resolution. Last week, when we discussed resolution, we mainly focused on the physical limit, on the diffraction limit. But in reality, the resolution is not only affected by the fundamental physics. There are other things as well when you try to focus the beam. So the resolution, if we expand it, it's written as square root resolution from diffraction. That's called dd square plus dg square plus ds square. Let's look at each these terms one by one. So dd is the diffraction limit. And we talked about it, our good old friend, Rayleigh, so Rayleigh criterion. I will not go through this again in details. Then we have the second term, it's called dg. This is the Gaussian diameter. This is because whenever you focus the beam, if you look at the beam profile always has the Gaussian distribution. That's, let me just draw the cross section. Your beam more like that, and this is the beam traveling direction. So you have the Gaussian diameter, and also you have the ds. ds, the name for that is called disk of least confusion. It's a function, ds is a function of spherical aberration. The purpose of writing this down is not to ask you to memorize what's going on, but I want to convey the information. Like when you can calculate the limit, the resolution limit, it's the upper boundary you can achieve. You cannot go over that. You're always within that. But in real life, it's never like that simple. You do the best to achieve the diffraction limit, then you can get the resolution. There are other things can play a role to degrade the resolution. For example, the imperfection of the lens system, the nature of the Gaussian profile of the beam. So resolution is affected by many, many factors. In this case, like we only listed 3. There's another thing I've got to mention when we discussed the Gaussian diameter. If we look at the Gaussian diameter, the tungsten gives you, the first tungsten filament, it gives you the worst Gaussian diameter because the beam is so spread out when they come out, when the electrons are coming out from the filament. Then in the cold vac, it has the best Gaussian diameter or the smallest Gaussian diameter. So in both cases, tungsten and cold vac, in terms of electrons, if they travel at the same speed, then in theory, they should have the same resolution. But the choice of filament can make a difference. So as a scientist, you do the calculation using the Rayleigh criterion. You calculate the resolution limit. But as an engineer, you have to think a lot more than that. Any questions before we switch to the PPT? I know we went a bit over time, but I'll try to finish everything within 5 minutes. Any questions? So today we looked at electron guns. All we have done so far, we are drawing the schematics. So what they look like in real life. Oh, okay, sorry. These are also schematics. So that shows the tungsten filament, the lab 6, and the FAG. The next micrograph, let's look at how they look like in real life. So the first one on the left, that's the tungsten filament. You can see it has like a hairpin shape. The one underneath is the lab 6. It's false colored. So you can see it's a single crystal. How the crystal grows is very fascinating. It just leaves like a really pointing tip. By applying heat, by applying electric field, electrons can be extracted from the very tip. Then the 2 images on the right, those are the field emission guns. You can see how pointy, how sharp the tips are. We talked about field emission. I want to move one step forward to quickly introduce you. Oh, zirconium oxide, I think it does some insulation stuff. I don't really know the use of zirconium oxide on the gun, but this is the electron gun, and electrons are generated at the very tip. Okay, we talked about field emission, and by applying a very large electric field, by applying a very large voltage, you can generate a very large electric field at the tip. Not only you can generate electrons, you can also kick out atoms one by one. That's how atom probe works. So in atom probe, you have something very similar to the field emission gun. Then in addition to applying the high voltage, you also apply laser pulse. And by doing that, you kick atoms one by one out of the surface. On the right-hand side, you have the position sensitive detector. And by looking at the mass to charge ratio, by looking at the position where they hit, then you can create a 3D maps of atoms. So let me go to next slide to speed up a little bit. So those are some data sets I collected when I was a PhD student. On the left-hand side, you can see the atoms, they don't distribute uniformly. They formed solid cluster. If you have a closer look in the 3D view. In the example on the right, we captured a grain boundary. You can see there's carbon segregation along the grain boundary. You get a true 3D view. What I want to say here is what we learned, what we are learning here is fundamental physics. By applying the fundamental physics like field emission, that simple concept, then you can expand that into field emission guns in SEM, in TEM, as well as atom probe. So translating fundamental knowledge into an engineering world, you can do a lot of things amazing.